So let's start discussing about refraction seismic. As we mentioned earlier, refraction is the phenomenon that happens when a variation of velocity creates a change of direction of the wave field. We can place a source at the surface and we can generate SH waves. I'm talking about SH waves because we are trying to measure the shear wave velocity of the subsurface. And we can generate different types of shear waves. And the second letter of the SH or SV denomination of these waves refers to the polarization. The H indicates the horizontal polarization. We create these waves with the specific sources at the surface, and we observe the wave field at different increasing distances from the source. And we might have different components of this wave field. Some direct event traveling directly into the first layer, directly from the source to the receiver, telling us what is the velocity of this first layer. And then we have some form of energy going down, being critically refracted by the top of layers with increasing velocities. We will see in a moment how this phenomenon happens. And this energy will be refracted critically, will travel parallel to this layer and will come back up to the surface, telling us what is the velocity of this layer. So the technique consists of generating, observing shear waves, identifying the arrival travel time, and interpreting this travel time to get the velocities and the thicknesses of the different layers in the subsurface. So the principle is that a seismic wave going down and hitting the interface between two media with different velocities will be reflected. So we have an incident angle I going down to the interface where the velocity and the mass density might change, and we have a reflection with an angle R, reflection angle. The incident and the reflection angle are exactly the same. And then we have a transmission angle, T, which is also called a refraction angle. Typically the angle with respect to the normal to the interface increases for an increasing velocity. The Snell's law is the one that defines the relationship between these two angles. And what happens is that when we have a source at the surface, the energy is going down in all directions, and at least one angle will hit the interface with a critical angle. And this critical angle corresponds to a critical refraction, which is parallel to the layer and comes back to the surface. So let's see what happens. We have a seismic source at the surface, we activate the seismic source, and we have the wave field propagating down. This is the direct wave that goes down into the earth, but also parallel to the surface. As soon as we touch the interface, we have a reflected wave that will come up to the surface with the same velocity in the overburden and a faster velocity in the layer below. So the angles will change because of the higher velocity and the different shape of the waveform. But part of this energy, which is traveling on top of the fast layer, will be critically refracted. So when you look at the different events that you can observe in this simple acoustic simulation, you can see the reflected angle equal to the incident angle and the refracted angle or the transmission angle. And you can see the head wave, the wave which is supported by the fast event going into the deeper layer, which is recorded at the surface with an apparent velocity. So the method works particularly well when we have large velocity contrast and we can observe directly into the records this change of dip. When you look at this record here, the one that you see at the bottom of this cartoon, you see that for more or less half of the spread, for more or less half of the receivers that we have deployed, we see an alignment of the first arrival, which has a certain velocity, a certain dip. And then, starting from a certain point, which in this case is more or less half of the spread, we have a sharp and abrupt change of dip, which means that the arrival time, as a function of the offset, changes less. The velocity, the apparent velocity is higher. This change of dip is what we have to understand and see to estimate the thickness and the depth of these layers. The acquisition can be performed with different techniques, and is probably the most critical aspect of this method, because it will impact also the possibility of using long offsets and having larger penetration. Typically, we need to generate shear waves, horizontally polarized, so we need a source which is able to transmit to the ground shear, strain, and stress. We don't want to have too much compression, so the ideal coupling is purely by friction. We use a long body, typically a sleeper, a railway sleeper, or what we call a shear beam that is just pressed onto the ground. We try to put some weight on it to increase the friction coupling, and we hit laterally the source. An alternative is using shear micro-vibrators. So vibrating sources that are again coupled to the ground purely by friction, and in which a reaction mass moves horizontally to transfer this horizontal motion, stress and strain, to the subsurface. There are some large-scale implementations of these techniques. There are some very old photos of very large hammers that are hitting laterally a shear beam, and there are modern shear vibrators that can be used to generate large energy shear waves into the subsurface. You can see in this video an example of a very large shear vibrator. This machine is more than 20 tons in weight. The base plate is pushed to the ground with a set of hydraulic actuators, and the coupling in this case is ensured also by some specific shapes of the base plate. Once the plate is in place, a reaction mass will start moving, and you will see in a moment that there is an accelerometer that will start moving horizontally. You can guess and understand that there is a horizontal motion. You will not see it as soon as we move to higher frequencies, but you have seen clearly that some horizontal forces is transmitted to the subsurface. So, summarizing, we need to create shear waves, SH waves. We use a horizontally polarized source. If we do not have a vibrator source, we use an impulsive source onto a shear beam, and we typically reverse the polarity to create shear waves with opposed polarities, while the compression waves will stay the same. Then the reverse of the polarity can be exploited to identify better the shear waves in data and identify which are the phases that correspond to the first arrivals of the shear waves and the refracted arrivals of the SH waves. Then the processing will consist of picking the first arrivals, identifying on different traces the travel time corresponding to the refracted SH waves, and building the travel time offset curves that can be interpreted and inverted and processed to get the thickness and velocities of the different subsurface layers. Then we might push the exercise to a geological interpretation, saying that we have sediments and a certain types of rocks based on a prior geological knowledge of the area. In all these schematic representations, we have always seen flat and parallel layers. The reality can be, and is often more complex. A simple example is, for example, a dipping layer, where the interface which is creating the refraction is not parallel to the topography and to the surface. In this case, we have apparent velocities recorded on both directions. And in this case, it is essential to have reciprocal shots producing the energy on the downgoing direction and the upgoing direction. We will record, therefore, two different intercept times on the two sides of the spread, and two different apparent velocities, a down dip and an up dip velocity. The processing and interpretation techniques can be more complicated. There are techniques which are based simply on the interpretation of the intercept times, techniques that use a higher redundancy, like the plus-minus and the reciprocal methods. But the method can be pushed to a higher complexity and reconstruct complex subsurface geometries. The principle is that we deploy sources and receivers at the surface. We record all the possible combinations of shot and receiver positions. This will correspond to multiple rays that will go down into the subsurface, will cross the section that we want to characterize at different positions. And we will be able to model, to simulate these rays into a numerical model based on the subsurface velocity until we find an ideal match, an optimal match between the model travel times and the peaked travel times. We need a higher redundancy, so we need many more shots and receivers at the surface, but then we are able to reconstruct complex geometries with sharp lateral velocity variations. We can identify weak zones, we can identify all the different features that might be of interest for the geometrical characterization of the subsurface. And in some cases we can overcome the need for high velocity contrasts. The limitations of this technique, SH refraction technique, are associated to the fact that we need refractions at the surface. So in some cases we need contrasts if we wanted to interpret data finding linear portions and branches of the travel time offset curves. This constraint can be relaxed a bit if we use tomography techniques. But in general we need an increase in velocity with depth. If the velocity does not increase with depth, the energy does not come back to the surface. If we have a velocity inversion, a fast layer resting on top of a low velocity layer, then the energy dips down at the base of this layer, and simply there is no information coming from the base of the high velocity layer. So there is an intrinsic ambiguity, because if velocity inversions are present, they are not really reconstructible with these techniques. Then there is a third and more subtle pitfall, which is associated to the presence of a hidden layer. In some cases, the velocity contrast is so large that it might be faster to be refracted twice and travel on the deeper, for example, the third fast layer, than traveling on top of the second layer. So the observed travel times will show us the direct arrival and directly the third layer. No evidence of the second layer will be present in data. And it's something that can happen when we have a large velocity contrast, and we should always think that our velocities and depth might be slightly different from what we have seen in the data. The investigation depth is one of the critical points of this technique, because typically, as a rule of thumb, to investigate down to a certain depth, we need from 3 to 5 times longer spreads. It means that if we want to go down to 30 meters, we might need more than 100 meter receiver length, receiver spread length. And it's not only the surface logistics, the need for having enough open space to deploy a long array. It's also that we need to send energy with enough signal-to-noise ratio up to this longest offset. And the energy of shear sources, of portable shear sources, sometimes is limited. And at noisy sites, it might be difficult to acquire data that will provide enough information to reach the desired investigation depth.